Good morning, everyone. It's my pleasure to be here to present my work on the tumors of fat. And my name is Binghao, and I'm currently doing a PhD in computer science department at UCL, University College London. And today I'm just covering some introduction of the fatty tumors. And I'm just go through with all of you the data and workflow of my research, and also I'm just cover some of the future work. So here you can see there are two typical examples of the fatty tumors. On the left-hand side, it is a typical benign sample, which is a lipoma, and on the right-hand side, it is a malignant sample, which is called liposarcoma. So both of them are made of fat cells, which we could find there are a lot of white spaces, and they do look very similar on the face of it. However, even by eye, from this magnification, we can find it is more cellular for liposarcoma compared with lipoma, and there are some architectural features here, which we call septa, and also we've got some atypical or aberrant nucleus in the liposarcoma. So in the real world, it is very hard to differentiate benign from malignant for the fatty tumors. Sometimes pathologists will do a additional genetic test to make the distinguish of the benign from malignant. So my project is to investigate how computational approaches can be a useful modality to differentiate benign lipoma from malignant liposarcoma. And here's the data I use. I've used 87 whole slide images. 32 of the 87 was benign and 55 was malignant. From the structure, you can find I've got a lot of variation, either in histology variation or artifact. Additionally, I've got the genetic test result as well as clinical information together with other informations. But I will just explain it in the feature slide. In real world, pathologists were usually looking at these two kind of features. The first one is, like I said, architecture feature. We can see here there are some structure features which we call septum. And the other one is nucleus feature, because unlike other types of tumor, for liposarcoma, the aberrant nucleus are different, which we can see it is very dark and large and have some irregular shape. In order to capture these two kind of features, I designed a workflow like this. So there are two main parts of the workflow. We can see the first part is a tile-based or patch-based training on the magnification of times 10, and the second part is on the magnification of times 40, which is to capture the nucleus feature. And today I'm going to cover this part only. So the first step for tile-based classification is to tile the image. And here is an example of a malignant liposarcoma host line image, which was done by Toxlin and Nielsen. And you can see there are a lot of white spaces, and the boundary is very hard to distinguish even by eye. Therefore, a pathologist just use a marker pen to highlight the boundary of the tissue. And after tile it just looks like this, and all the further training or testing are based on the tiles. Here are some examples of the benign and malignant tiles. And here are some examples of the histology variation of the tiles. For example, I've got some conventional, I've got fat necrosis, and vessels and muscles, and fibrous tissue, fibrous septa, or some lymphocyte. Apart from it, I've got some invalid tiles, which contain some artifact information. For example, the marker pen, pathologists will usually use it to highlight the boundary or the region of interest in the host line image. And I've got some dust or bubble-like or some glue-like. Or here I've got even some unknown features at the background. You can see there are some architecture at the background, but currently I just don't know how it originates. So currently I'm trained on approximately 300,000 tiles and test on a dependent set containing of 24,000 tiles. And I've got a overall accuracy, reasonable overall accuracy at about 90%. So here is a tile level testing result, which means there are about 90% of the tiles was correctly predicted to be malignant or to be benign. However, pathologists will not make the diagnosis on the tile based, on the tile level. pathologists will usually make the diagnosis or prognosis on a host line image level. In order to do the host line image level testing, I developed a metric which is called malignant score. So the malignant score for every tile means the probability of this tile to be malignant. And here I then plot the distribution of the malignant score for all the tiles in every host line image. And here are 3 examples. For example, the first one, what you see, the majority of the tiles have a very low malignant score, which means the majority of the first sample is benign-like. And very little tiles in the first sample has a high malignant score, which means this kind of tiles are malignant. And after we choose a threshold of 0.5 as a start point, we can then calculate the malignant score of every host line image. For example, the first one, we've got 0.238, which is a very low malignant score, and this stands for the first host line image is likely predicted to be benign. And the third one, which have a very high malignant score on host line image, which means this host line image is likely predicted to be malignant. And I've also got some very uncertain case, which look like this. You can see there are 2 peaks, and there's one peak around 0, and there's one peak around 1, which means it is very hard for the CNN to tell whether it is benign or malignant. I then plot a heat map. The reason for the heat map is I can map the malignant score for every tile to the origin host line image. For example, here you can see there is a very heat area, which refers to this area here. Which means this area is most likely to be malignant. However, the cool tiles, for example, the black tiles here, which means this kind of tile is most likely to be benign. And this heat map also gives some confidence for pathologists to recognize or double confirm whether this kind of workflow or algorithm do works on lipoma or fatty tissues. I then did the same experiment in 20 totally independent host line images. As you can see here, there are 2 lines. So every dot means every sample, and here is the accuracy from 0 to 100. You can see most of the samples was correctly predicted on host line image level. However, I've got 1 in lipoma and 1 in well-differentiated liposarcoma, which is very hard to tell. And if you see here, there's the host line image of the uncertain case, which contains a lot of fibrous tissue, fibrous septa. And I've also got 2 out of 10 was wrongly predicted in the malignant case, which looks quite similar to the benign case. So currently my work is just like a good start point, and there are a lot of future works that need to be done. The first one is some optimization of the first part, which is tile-based, can be done to increase the accuracy a little bit. And the second part, we just integrated some handcrafting feature selection together with unsupervised learning here and the CNN here to capture the nucleus feature. I believe if we just integrate the CNN2 together into the system, the overall accuracy or the overall performance can be largely increased. Also, pathologists take a very important role in this project because we take pathologists into our workflow loop. For example, here and here as well. We'll get some feedback from pathologists to improve our algorithm. And also, we just like to have a test for the generalization. For example, whether this workflow or this algorithm do work on external data set. So in conclusion, I'm doing a project on fatty tissues using a combination of computational approaches such as deep learning techniques or unsupervised learning. And the current result shows the CNN or computational approaches do work to differentiate a benign lipoma from malignant well-differentiated liposarcoma. And there are some future work which can give this workflow some improvement. And at the end, I would like to thank my supervisors, Dr. Kevin Bryson and Dr. Nishilin Pillay, to give me a lot of support with my PhD training. And also, I would like to thank RNOH, which gave me a lot of samples of the tumors of fat. And I would like to thank UCL Cancer Institute, who just scanned all the slides for me. And thank you all for your attention.
Are there any questions? Yes.
Interesting talk. In your heat map,
Yep.
on the background, there's a huge variability. So can you explain why, particularly on the background, which there should be uniformity, you have such a large variability?
Yes, it's a good question. In fact, people usually will apply a mask, at the boundary of the tissue. However, there are two cases. The first one is, for most of the case, the boundary is very hard to detect, and I'm currently work on it. And I believe if you just mask, all the background or invalid tissue, then the accuracy can be largely increased. So as I said, this is just like a starting point of the project, and we're just working on the background issues.